Yeah. Hi. Hello. Good morning, everyone in the US. Good afternoon to everyone in Europe. Um, we are, after some break, restarting our must seminar series, and it's my pleasure to introduce for the first seminar of this year uh, um, Chris Woodgate, and he'll be talking to us about work on CPA concentration wave theory for alloys. Chris got his PhD at the University of Warwick in the UK under the supervision in the group of Julie Staunton, and he completed his PhD about 2 years ago. After this, he had a postdoc position that I understand he shared between different places, both at Warwick and at Northeastern and University of Delaware here in the US. Uh, since last summer, he he has held an EPSRC doctoral fellowship at the uh, University of Bristol, and he continues to be at the um, uh, University of Bristol. And it's my pleasure to welcome him to give the seminar today. Looking forward to your most interesting talk.
Okay, great. Well, thank you very much for the introduction, Marcus, and thank you for inviting me to speak. So I will share my screen now, I think, if I click this button. And then if I make this full screen, hopefully we should be good to go. Uh, can everybody see that okay? Yeah, perfect. Okay, great. Yeah. So I am going to talk about some work that we've been doing, um, looking at studying the phase stability of multi-component alloys with a particular focus on the high entropy alloys. And the methodology is based on the multiple scattering theory type methods. Okay, so we're going to use the coherent potential approximation to describe the internal energy of the disordered alloy, and then we're going to consider uh, chemical atomic scale chemical fluctuations being described by what are known as concentration waves. Okay, so let me make sure I can go forwards. Here we are. Perfect. So the plan for the talk is first up, I'll give a little bit of background. So I'm going to talk about, just for a general audience, that the basics of what we mean when we're talking about alloys. I'll then focus a little bit on the high entropy alloys, so talk about what makes those special. Um, and then I'm going to outline some of the challenges that come with trying to simulate the phase stability of alloys, and particularly multi-component alloys. Then I will outline the approach that I've just mentioned there, so using concentration waves to describe these atomic scale chemical fluctuations, and trying to sort of learn about the thermodynamics and phase stability of alloys using this method. And then sort of in the second half of the talk, I'm going to present some case studies. Okay, so I'll start off by talking about a family of high entropy alloys known as the refractory high entropy alloys. I'll then spend some time talking about the Cantor alloy and its derivatives. Okay, so this 5-component chromium, manganese, iron, cobalt, nickel, and various systems where selected elements have been removed from that composition. And then right at the end, if there's time, I'll talk a little bit about the addition of aluminium to some of these systems. Okay, so what happens when you add in aluminium, because this quite often promotes the formation of intermetallic phases. And then at the end, I'll summarize, and I'll give an outlook on maybe where we're looking to go next. Okay, good. So fine. A bit of background on alloys first, because I don't know quite what the level of the audience is, and I thought it was good to sort of lay the foundations. So first up, why are we interested in alloys? Well, um, I guess really the answer is that so many of the materials around us are alloys in some sense or other. Okay, so there are various structural materials which are alloys, things like steels, aluminium-based alloys, titanium-based alloys. Um, Sometimes we look at we look to alloys to give us materials which are resistant to corrosion. So, for example, stainless steels. Um, there are various magnetic materials that are alloys. So things like transformer cores, permanent magnets are alloys quite often of rare earth elements with transition metal elements and similar. Magnetostrictive materials, things like galvanol, a highly magnetostrictive material is an iron gallium alloy. And then also things like semiconductors. Okay, so when we think of alloys, quite often we think about metallic materials, but actually we can have semiconductor alloys as well. So and that can enable us to sort of fine tune band gaps in semiconductor materials. Okay, so when I say alloy, what do I mean? Okay, well, an alloy is a mixture of typically two or more, usually metallic elements, although as I've said, you can consider semiconductor alloys as well. Um, and you can have substitutional alloys. Okay, so you can have a fixed underlying crystal lattice where you've got some probability distribution determining which chemical species are sitting on which lattice site. Or you can have interstitial alloys. So this picture in the middle at the bottom here, where um, where you have in a sense you have little smaller atoms squeezing into gaps between lattice sites. Okay, and an example of that would be something like the addition of carbon to iron or to steel. And of course, you can have the situation where you have both. So a stainless steel quite often has carbon in it, and so I've got a mixture of iron, nickel, and chromium on the lattice sites, and then I have carbon squeezing into the gaps. Okay, but today I'm only going to worry about substitutional alloys. I mean, in principle, we can do interstitial alloys, but we just haven't got around to that yet. So everything I talk about today is going to be substitutional. Okay, and then if I have a substitutional alloy,
May I just ask a question, a short question here?
yeah, please fire away.
You would one would guess naively, maybe I'm naive, that if you have interstitial alloying, that the lattice relaxation effects are much more pronounced. Is this generally correct or true or?
Yeah, I mean, yeah, you're right. You would expect some local lattice distortions depending on how big the elements going into the interstitials were, for sure. But similarly, if you have a large size mismatch, even if you have a substitutional alloy, if you have a large atomic size mismatch, you can have quite substantial lattice distortions there as well. Yeah.
Okay.
But no, you're right. Yeah. Local lattice distortions. Yeah, there's this assumption that there's a perfect underlying lattice, but of course, when there's size mismatches or when there's atoms in the interstitial region or even when there are vacancies, then yeah, there are these local lattice distortions. Yeah.
Thank you.
No, thank you. Yeah, okay. So if I have a substitutional alloy, then I might worry about how the atoms are arranged on that lattice. So the conventional picture of a disordered alloy, or what we call a solid solution, is this situation where essentially the elements are distributed at random. In alignment with the overall concentration of each element present in the composition. Okay, so if I have a 50-50 binary alloy, I would expect in a solid solution, each lattice site would have 50% probability of being occupied by either chemical species A or chemical species B. Okay, but in general, as I cool a material down, okay, what can happen is a level of atomic short range order can emerge, so little local correlations between pairs of elements. And then eventually I might expect to see some different structures emerging. So I can have an ordered intermetallic phase, or what people sometimes call an intermetallic compound, where there's some regular crystal structure that's appearing, where I can identify a meaningful primitive unit cell, which is what I've drawn at the bottom here. Or I can have a situation where there might be some phase segregation, okay? So where certain elements really just are not happy to mix. So an example of a phase segregating system might be iron copper. Those two elements really refuse to mix or alloy well at all. Okay, and what I'm going to talk about today is a methodology for modeling these kind of phenomena in the multi-component setting. Okay, so where in an alloy where I have three or more constituent elements. Okay, and you might say, okay, well, that's wonderful, but why do I care? And the reason you care is that actually in alloys, the arrangements of atoms determine their properties, okay? So these can be things like mechanical properties, so the bulk modulus, they can be electrical properties such as resistivities, which I'll talk about in a little bit. They can be magnetic properties, so Curie temperatures. And in the case of semiconductor alloys, there's evidence to suggest that actually different atomic arrangements can result in different optical properties, so changes in the size of the band gap. Okay, and the hope is that if we do modeling, if we develop modeling techniques for alloys and these sort of complex materials, we can explain what's happening experimentally. Potentially, we can offer new processing routes to experimentalists to help them control the microstructure. And eventually, sort of the aspiration would be that we could suggest new compositions with improved properties for a particular application. And, you know, I've sort of put the hint here. Maybe, you know, you're thinking about doing high throughput searches. If you have a nice computationally efficient method for doing alloy thermodynamics, maybe you can screen a large number of compositions to see which ones could be good materials for certain applications. Okay, before I get into the details of sort of the high entropy alloys and then the formalism we've been developing, I thought I'd give a quick example of an alloy phase diagram for the uninitiated. Okay, so I'm going to talk about one of the real prototypical alloy systems, which is copper gold. So you alloy copper, which is a 3D transition metal, with gold, which is a 5D transition metal. And on the right here, what you're looking at is an alloy phase diagram. Okay, so along the x-axis, I have the concentration in terms of an atomic percentage of gold. Okay, so the left-hand end is pure gold, the right-hand end is pure copper. And then, you know, in the middle is 50% copper, 50% gold. And then on the y-axis, I have temperature, and this is in degrees Celsius in this case. And so at very high temperature, there's a liquid-solid coexistence curve. Okay, so this is where the alloy essentially is melting or solidifying, depending on whether you're cooling it or heating it up. And then there's this big region here where there's gold, copper, and that's denoting this solid solution. Okay, so this situation where the atoms are substituting for one another randomly. And if I look, okay, specifically at the 50-50 composition, if I imagine cooling my alloy from the melt through into this solid solution phase, eventually there is a transition marked here. Okay, and what's happening there is that it turns out that it's no longer favorable for the atoms to form this disordered FCC phase. Instead, the thermodynamically favored phase is this L10 phase, where actually the copper and the gold atoms are forming layers. So there's still underlying FCC lattice, but there's alternate layers of copper and then gold and then copper and then gold and so on.
Just one question in the solid solution region. From what I heard, I mean, we have a little group in Florida State University that are dealing with alloys, and what I heard from one of my engineer colleagues who uses them for applications, that these atoms, you know, in the solid solution, they are not really frozen at some elevated temperatures, but they migrate. In other words, you can say that there is a lattice on which they are moving, but it's really not like an amorphous. It's like a liquid in the sense that these individual gold atoms, they actually diffuse.
Yeah,
now,
yeah,
how
for
much
sure.
is how much is known about this?
Well, I mean, you know, quite a bit actually. So I'm working on a project at the moment looking at a particular binary alloy where we can model atomic scale diffusion. Those processes are generally mediated by lattice vacancies. Okay, so the way I like to think about alloy elemental diffusion in alloys is if you think about those puzzles you have where you have like, I don't know, a 4x4 grid of squares with one square missing. Okay, and you think of the vacancy as the square that's missing, and what you can do is push the squares around and gradually change the picture. And so what's happening? Yeah, at any finite temperature, there is a level of atomic diffusion that's going on. So you still have the fixed underlying lattice, but these vacancies, they mediate a diffusion process where atoms can swap into vacancies. And so the vacancies are essentially sort of quite mobile. And by moving through the lattice, they can cause the atoms to rearrange themselves.
But my question, I'm sorry to interrupt, but my question is this. You can imagine that the vacancy, there is a process, you go from one lattice unit cell to another. This is an elementary process, and that's all you need to know. But it's really, you know, by the analogy to supercooled liquids, there are collective motions, and you may imagine that if you can reach low enough temperatures by supercooling, then there is a dramatic slowing down because there are collective motions, like a glass transition can happen.
Oh, I see what you mean. Yeah, okay. So indeed. So I talk to I have a theory colleague who works on glasses, and he tells me that alloys are just glasses. And in a sense, yeah, if you want to think about it like that, they are. So what you know, if you think about it in the right way, and I say that because what you can do is you can take a solid solution phase and you can quench it. And then what you can do is you can freeze in the equilibrium state at high temperature. And as you say, I've cooled the system down enough that my vacancies are essentially frozen, and I've cooled in that solid solution. I've frozen in that solid solution phase. And that's quite a common processing technique. Yeah.
Okay, very good. Thank you.
So no, yes. So absolutely, yeah. So maybe a good take home from this is that just because the equilibrium phase at 200 degrees Celsius is this L10 copper gold phase, actually, if I take my alloy at 800 degrees Celsius, where I'm comfortably in the solid solution region, and I quench it down to room temperature, actually probably is in the solid solution phase if I do that quickly enough. Yeah.
Right. So that means that these phase transitions that you drew here,
fine.
they're actually first order transitions.
So we've had a little bit of discussion about alloy phase diagrams. They are usually first order, but not always. It depends on the crystal structure that you're starting from and going to. But yeah, very often they are, yes. Yeah. Okay, fine. So we had some discussion about these alloy phase diagrams. Okay, and what I wanted to highlight was that actually how these phase diagrams, how the different phases have different properties. And the example I wanted to highlight was of residual resistivity, because it's quite a nice fundamental property of a material. Okay, and if I take the L10 intermetallic phase, this thing that's stable at low temperature, or thermodynamically favorable at low temperature, and I do a density functional theory calculation. This is using the KKR method, and here I'm looking at the band structure. In the middle, the density of states, the electronic density of states on the right, and then, okay, on the left, I'm just illustrating the L10 structure. I see that, okay, I've actually plotted the Bloch spectral function here, so there's a small imaginary component to the energy, so the bands don't look quite pristine, but believe me, if you take the limit of zero energy, you have pristine, perfect band structure. And in principle, you have zero residual resistivity. If you cool the system down to 0 Kelvin, your Bloch states are eigenstates of the Hamiltonian, and my electronic mean free path is in a sense infinite. Okay, but if I look at the disordered FCC phase, okay, so what's known as the A1 phase, and here I've done a KKR-CPA calculation where I'm using the CPA to describe the electronic structure of the disordered alloy. What I see is that my band structure becomes really heavily smeared, because if I imagine I'm an electron propagating through the material, I'm not seeing a regular periodic arrangement of atoms. As I move through the material, I might see a gold atom, and then suddenly I encounter a copper atom. And in a sense, although I have this underlying crystal lattice, the periodicity is broken because of the changed chemical identities of the different lattice sites. And what this means is that even if I cool the material down to 0 Kelvin, the Bloch states are no longer eigenstates of the system, and there is a finite electronic mean free path, and therefore a finite residual resistivity.
Right, it's incredible how the mixing of the bands is confined to this strip where you have many bands, and then at high energy or even a rather Fermi energy, there is very little mixing and broadening of these bands, right?
Yeah, okay, and yeah, it is interesting. Yeah, and the reason that happens is actually because a lot of the disorder, if you like, in a sense, the SP states, the sort of the dispersive kind of more free electron-like states, are fairly similar for both copper and for gold, and the real difference is in the D bands, which is this band of smeared out states in the middle here, and essentially what you can see on the right, okay, you can see that copper has a fairly narrow 3D band, whereas gold has a wider 5D band, and so the reason the smearing is so heavy in the middle is because of this mixing of the 3D and the 5D states in some sense. Yeah. Okay, and so experimentally you can go away and you can measure a residual resistivity, and this is actually hinting back at what we were just talking about. So if I take here, I'm looking at, I think bizarrely actually the copper and the gold have been flipped around in this figure, but this is some experimental data. If I quench the solid solution from high temperature and I look at the residual resistivity, I get these triangles, this dashed curve here, so I get this kind of nice parabolic behavior where at pure copper or pure gold, my residual resistivity, I have a pristine crystal, it goes to 0. And in between the two, it kind of has this kind of x1 over x1 minus x parabolic type dependence. But if I look at the squares, these are samples which have been annealed. Okay, so they've been baked at a particular temperature below the disorder ordered transition temperature. And what I'm seeing is either L10 at the 50-50 composition or L12, which is a cubic sort of related structure appearing. And there I see that my residual resistivity drops quite substantially. It doesn't quite go to 0, presumably because the material never gets perfectly ordered, but it drops a long way. And so this is an example of how the arrangements of atoms in an alloy can really affect their properties. Okay, good. So we've spoken a little bit about alloys and talked about what we mean by phase stability and how this can affect various materials' properties. But now let me sort of start to get into the meat of the talk and highlight the systems I want to discuss today, which are the so-called high entropy alloys.
Before you move forward, sorry, may I ask a
Yes.
short question? Yeah.
Please
So
do.
one thing is you show a short range order reading, right? What does that mean in that picture?
Oh yeah. Okay.
Here.
Yeah, the short range order region. Yeah. No, you're absolutely right. So what happens really, okay, is you don't quite have the situation where you have a completely disordered system that immediately goes to this perfectly ordered system. What actually happens is as you approach these transition temperatures, as you approach, the L10 transition temperature, what you find is that locally certain atoms prefer or dislike, so they like or dislike certain pairs of atoms nearby. So you have
so that
some
is
kind of
the
finite
region about the order, the L1, 2, and B turn A1 somewhere, right? Between melting temperature and the order. I see you have some solid line, right? Above the solid line, right? And then below the melting temperature.
Yeah,
Some reading,
exactly.
right?
Yeah. So yeah, I mean, this is not my figure. This is a figure I pulled from an experimental paper. You imagine as you cool the material down, from you start off from the liquid, and essentially you have minimal short range order at very high temperatures, and then as you approach the transition, these sort of atomics, the short range order in a sense will grow until you reach the temperature at which the transition occurs, and then long range order begins to establish itself.
Just one point. If the transition is first ordered, then the correlation length associated with short range order should not actually diverge, but remain finite.
Well, okay, indeed, yes, yeah.
So what is the typical value of the correlation length for this short range order? How short is the order?
I mean, from experience, you would expect this to really, you're talking the first few sort of, if you like, coordination shells of your lattice. Okay, so you're seeing at nearest neighbors that there are quite strong pair preferences. Maybe at second nearest neighbors there are some pair preferences, but yeah, it's not long ranged. I mean, it can be, but in general, you would expect it to be reasonably short ranged. Yeah.
Very good explanation. Yeah, very good. Thanks. So just to make sure I understand all this correctly, so these are based on this or electronic disorder, right? We don't include anything related to, let's say, lattice distortion or some other vibration stuff, right? We included that part in this talk. Am I right?
So for the most part, I am thinking, so when I'm talking about disorder, what I'm thinking about is the substitutional disorder on lattice sites and how that changes, as you say, how that introduces this smearing, this kind of disorder, this electronic structure of the disordered solid solution. I mean, in principle, you can include vibrational disorder and so on, if needed. In this approach, you've got vibrational entropy terms, for example, and how they alter the transition temperatures. But generally, what I'm thinking about is having a configurational entropy describing the electronic structure of the disordered solid solution, and then seeing how my free energy changes as I apply atomic scale chemical fluctuations.
Good.
Okay. Yeah, great, fine. Okay, so let's get back into it. So today I want to talk about high entropy alloys, and I thought I should briefly introduce those before we got into the meat of the subject. So high entropy alloys, okay, what are they? Well, I've been highlighting these examples, okay, of traditional substitution alloys where I have 1 to 2 base elements and maybe small additions of other elements at low concentrations. Okay, but in the sort of early to mid 2000s, this concept came about, so-called high entropy alloys. So there were these two kind of seminal papers published in 2004 by pretty much concurrently by 2 different experimental groups, where they showed that for certain combinations of elements, it's possible to stabilize single phase solid solutions containing, some people say 4 or more, some people say 5 or more, but I generally just say 4 or more elements in near equal ratios, so where the concentrations of each element are near equal. Okay, and it turns out that if you write down a toy model of your free energy, this large number of elements present in the composition means that you have a large entropic contribution to the free energy. So Ts here, this is the entropic term in my free energy. Okay, Boltzmann constant temperature, and then a sum over alpha, a chemical species. C alpha is the overall concentration of each chemical species. And the sum over alpha, C alpha, log C alpha, gets larger as the sum over alpha runs over a large number of elements at lower concentrations. And so there are certain combinations of elements where this entropic term is perceived to help to stabilize a single phase solid solution that might not otherwise form.
So this formula actually applies to infinite temperatures, really, where the entropy is completely I mean, the configurations are all equally probable, right?
The expression I've written down is in a sense for the limit of a perfectly disordered alloy. But what I'm going to talk about later allows for there to be atomic scale chemical fluctuations. So I write this down because it's a nice simple form that people can wrap their head around. But later we account for the change in entropy induced by atomic scale chemical fluctuations. Yeah. Okay, so then you can ask the question, well, why are we interested in the high entropy alloys? And it turns out basically that very often these materials have superior properties for applications. So some of them are very good at resisting being irradiated. Some have excellent fracture resistance. Some examples have been shown to have really good performance across a wider temperature range than many conventional alloys. So they're kind of interesting for these, what people call advanced engineering applications, materials in extreme environments and so on. But I'm a physicist and I'm also interested, and kind of the reason I'm interested is because there's a range of interesting physical phenomena there as well. So they have quite interesting electronic structure. Stephen Dugdale, who sits upstairs from me at the University of Bristol, he measures the Fermi surfaces of materials. And, he's got some nice work showing that the Fermi surface in these materials can be very, very heavily smeared on account of the chemical disorder. Some of them have interesting magnetic properties. There are certain examples which have been shown to exhibit superconductivity. And so they're kind of interesting to physicists as well. Okay, so we're interested, but we want to know about the phase stability. So if I have a given combination of elements, I want to know, am I going to have a completely disordered solid solution? Am I going to have some local short range order? Or am I going to have some intermetallic phase emerging? And those are the kind of questions we're thinking about answering in this talk. Okay, but there are challenges associated with this. Okay, so for a start, if I have an alloy with multiple constituent elements, the size of my configuration space, if I consider a simulation cell containing a finite number of atoms, the size of the space of possible configurations grows kind of combinatorially with the number of elements present in the composition. Okay, so I have this real explosion in chemical complexity, which means that I need to sample a lot of configurations to make sure that I'm getting sort of thermodynamically representative information. Okay, so this is a nice figure showing the number of possible local chemical environments within a certain cutoff region as compared to the number of alloying elements present in the composition. The other thing is, okay, I said near equiatomic. If I'm tweaking the concentrations of particular elements, how do I handle potentially arbitrary concentrations of elements in my modeling formalism? And then if I have a system containing magnetic elements, so say this 5-component Cantor alloy, where all of those elements in their elemental form exhibit a magnetic phase transition, how should I be looking after magnetism when I'm simulating the phase behavior of the material? Okay, Well, the community's been working on this for a long time, and there are a number of solutions that are in principle available, okay? So we have these so-called semi-empirical approaches based on thermodynamic databases. So we're talking about things there like CalFAD, calculation of phase diagrams. What you can do if you're a computational person like me who prefers not to necessarily rely on these kind of semi-empirical databases, you can imagine filling up a simulation cell with the atoms present in your alloy and sort of shaking it up using some kind of sampling algorithm. And I kind of refer to this as maybe the ball pit approach. And there, the forces and energies on your atoms can be given by things like density functional calculations. If you have a really big supercomputer, you can use interatomic potentials, things like machine learned interatomic potentials, if you have a medium-sized supercomputer. And or you can use things like lattice-based models like cluster expansions, and they tend to be kind of the quite often the cheapest of the options, but it depends, precisely on what interatomic potential you're using. And what I'm going to talk about today are these kind of approaches based on effective media, where I consider, if you like, rather than having a ball pit full of lots of different atoms, instead I'm going to consider a situation where I construct an effective medium where, if you like, I try to describe the average properties of the disordered alloy and then see how the internal energy, the free energy of the system changes if I allow the partial occupancies of lattice sites to change. Okay, good. Fine. So I'll talk a little bit about the approach we've been using. So our starting point is to use the coherent potential approximation. Okay, so this is this well-known means in multiple scattering theory of describing the average electronic structure and consequently the internal energy of the disordered alloy. Okay, and the idea is that this is very computationally cheap because you can work with the primitive unit cell of the underlying lattice, but it turns out to accurately capture many details of the disordered alloy. And the beautiful thing is that if you want to simulate a material in its paramagnetic state, you can apply something known as the disordered local moment picture, which was pioneered by my PhD supervisor, among others, Julie Staunton, where you can consider averaging over many possible orientations of magnetic moments. Okay, so the coherent potential approximation gives us a means by which to describe the homogeneous disordered alloy, right? So if you like the infinite temperature limit of a solid solution where there are no chemical fluctuations, no chemical correlations whatsoever. But we want to look at phase stability, which means we need to describe sort of local chemical fluctuations. And the way we do that is using concentration waves. Okay, so this is a means by which to describe how these partial lattice site occupancies in my CPA effective medium are varying. Okay, so here's a 1D example of a concentration wave, okay, in a binary 50-50 alloy. Okay, and what I'm imagining is at the top, I start with this situation where all of my lattice sites have a 50-50 probability of being either of chemical species A or chemical species B. And then I'm imposing a chemical fluctuation using a concentration wave, which has wave vector pi over A. So it's a wave vector at the Brillouin zone boundary. And it has chemical polarization, delta C alpha. 1 over root 2 is just a normalization factor. +1 means that the concentration of an orange atom is going up. -1 means that the concentration of a blue atom is going down. So when orange is going up, blue atom, the blue is going down. And then when orange is going down, blue is going up. And this describes this alternating AB ordering. Okay, so that's very nice. And the beautiful thing is that not only do we have this, but we can learn about the energetic cost of these fluctuations using something known as the alloy S2 theory. Okay, so this enables me to assess the change in internal energy and consequently the change in free energy of the alloy due to an infinitesimal applied chemical perturbation. This is not the only way of doing this. There are other ways of doing this. There are alternative methods to the S2 theory. But one thing that's particularly nice about the S2 theory is that it fully includes the charge rearrangement due to an applied chemical perturbation. And it turns out actually in many of these systems that is quite important.
So is this the same as saying that if if I'm doing statistical mechanics of an Ising model, I can do what they call a Gaussian approximation? In other words, the order parameter fluctuates around its zero value, but
Yeah.
it fluctuates weakly. So to leading order, I can do a quadratic harmonic approximation around the uniform state, and I look at these leading fluctuations. This is like a Landau-Ginsburg theory.
Yeah, absolutely. Yeah. In
Right.
fact, I think in 2 slides' time, there's going to be the words Landau theory.
Okay.
So yes, yeah, in principle, yeah. So actually, there are 2 things. So we use a Landau theory for an initial estimate, but there's also the recovery of an effective pair interaction, which in principle.
Well, the difference between Landau and Landau-Ginsburg theory. In Landau-Ginsburg theory, they allowed that there's a gradient square term, so they allowed the order parameter to fluctuate weakly around the leading order fluctuations around the uniform state are described, right, by Landau-Ginsburg theory. So you can describe a correlation function of the order parameter field. And it seems to me that this is exactly what you're doing here, right?
Yeah, absolutely. Yeah, this is exactly what we're doing. Yes. Yeah.
Right, wonderful. Excellent. Thank you.
Okay, so before I move on, I just wanted to give you some examples. Okay, so this was an example of a binary, a concentration wave in a binary alloy. But let me talk about concentration waves in the multi-component setting, because I want to give you 2 examples here. So I'm going to give you 2 1D examples where the wave vector is the wave number describing the concentration wave is pi over a, but where the ordered structure is different. Okay, so the first example on the left is going to be this situation. This is now a 3-component alloy where I have 25% orange atoms, 25% red atoms, and 50% blue atoms. And on the left, I'm describing a situation where my concentration of my blue atoms is remaining unaffected, but my concentration of orange and red atoms is alternating. Okay, and this is described by this wave vector, this concentration wave with chemical polarization +1, -1, 0. Okay, and on the right, I'm describing a situation where now, instead of the blue atoms remaining disordered and the orange and red atoms alternating, here I'm describing a situation where the ordering is emerging between the blue atoms and the orange and red atoms, with the orange and red atoms being unaffected. And there the concentration wave has this different chemical polarization. Okay, so -1, -1, +2. And so that's going to be important in what I talk about in a little bit, because the chemical polarization tells me about how the different chemical species are partitioning themselves onto different lattice sites. Okay, so this is where we come at a Landau-type theory for the free energy of the system. So to assess ordering tendencies, what we do is we write down an approximate free energy. So omega is Ts minus mu n plus u. Okay, and in the theory I'm using here, Ts is this this sum over lattice sites of this entropy of mixing. Okay, mu n is this mu I alpha C alpha term. This is these actually act as Lagrange multipliers in the theory, but they're helping to enforce the overall concentration of each chemical species. And then U is the internal energy of the alloy as described via the CPA. Okay, and then what I do is, due to symmetry, the first derivatives of this free energy around the homogeneous reference state can be shown to vanish. And what I have to look at then is the second concentration derivative, and that means I build up an expression for a Hessian matrix. Okay, and it turns out, okay, you can do the concentration derivatives of the first 2 terms by hand pretty trivially. Okay, but the challenging thing to evaluate is the change in energy of the CPA reference medium, and that's what the S2 theory gives me access to. Okay, what I look at then, in some sense, is the eigenvalues of my Hessian matrix. Okay, and at high temperature, my Hessian matrix is strictly positive definite. All eigenvalues are positive, and the system is stable to chemical fluctuations. But at some finite temperature, I anticipate that there is at least one eigenvalue which passes through 0, which tells me that I've gone from a situation where I have a high-dimensional bowl of free energy to a situation where I have little local minima emerging, and the system can move into an ordered or partially ordered phase. Okay, and the nice thing is that in a sense, the eigenvector associated with the eigenvalue of the Hessian that's gone negative is telling me about the chemical polarization of the concentration wave. Okay, so if we think back to those ternary examples we had, what I want to do is just show you kind of what the eigenvalues of this Hessian matrix can look like. So we work in reciprocal space. Okay, so I wanted to show you an example here of a one-dimensional alloy. So same composition as before, 25% orange, 25% red, 50% C. And I'm imagining a situation where A and B have a like pair neighbor interaction of some constant V, which is greater than 0. A and B have an unlike pair interaction minus V, which is less than 0. So A and B prefer not to sit next to themselves, but like to sit next to each other. And C doesn't interact with AB or itself. Okay. And if you plot the eigenvalues of this Hessian matrix as you move around the irreducible Brillouin zone, in this case it's just a one-dimensional system, there are 2 eigenvalues because it turns out by enforcing the overall composition of the alloy, you remove a degree of freedom. And what you see is that the minimum eigenvalue occurs at the wave vector pi over a. This flat mode, I should say, is actually associated with the fact that C is not interacting with anything. So flat modes are associated generally with species which are weakly interacting. And if I work through the Landau theory, I find that my ordering temperature, KBT ord, is equal to V over 2. Okay. And I describe the situation exactly as I had on the left in that previous slide, where I want to get alternating AB ordering with C remaining disordered. Okay, so that's very nice. And so this Landau type theory gives me an estimate of the ordering temperature and allows me to infer the nature of the ordering. Okay.
I just want to mention that you can get flat modes also from geometric frustration, like on the Kagome lines.
Yeah,
they're example sure.
Yeah, so indeed, yeah. So you're right. Yeah. So the flat modes are not necessarily indicative always of species that are weakly interacting, but in this case, that is exactly what that flat mode. That is exactly why that flat mode is appearing. Yeah. Okay. So the second example I want to show you is sort of linked back to the picture we had on the right previously, where now I'm imagining that A and B don't interact, but A would like to sit next to C, and hang on, is that right? Maybe that should be B and C. Let me think about this. Okay, so I'm gonna go through to my picture. Yeah, okay, so A and B, they both want to sit next to C. Yeah, so this should be B and C, unlike pair interaction. But C doesn't want to sit next to itself. Okay, and if you work through the eigenvalue analysis, again, you find the wave vector is pi over A. This time, the Landau theory gives me a slightly different estimate for the ordering temperature, which is related to the entropic term and the concentration of each element present in the composition. But I find that this situation is describing this ordering where the blue atoms are moving to one sublattice and the orange and red atoms are remaining on the other sublattice but disordered. Okay, good. The nice thing about doing those derivatives of the internal energy as evaluated within the CPA is that actually they give me access. I evaluate them in reciprocal space for sort of for reasons to do with the translational symmetry of the underlying lattice. But if I back Fourier transform, if I go back to real space, I can recover an effective pair interaction. Okay, so an Ising-like interaction between atoms on different lattice sites in the alloy. So Vi alpha J alpha primed describes the interaction of an atom of species alpha on site I with an atom of species alpha primed on site J. And typically, okay, we were talking about range of interactions earlier. Typically, you find that these interactions are fairly short range. So you're talking the first handful of coordination shells before they tail off. And then what you can do is you can infer, you can look at the phase diagram across all regions because the Landau theory is only valid for inferring initial orderings. And so this is an example of an iron nickel platinum alloy that we studied. And so the Landau theory would give you the initial ordering at just over 1000 Kelvin. But by doing some kind of Monte Carlo simulation or using these effective pair interactions, I can see that there are subsequent additional orderings with reducing temperature. Okay, so yeah, Vi alpha is this effective pair interaction, and yeah, we can use various sampling techniques to explore the phase space. Okay, good. So a kind of a schematic overview of the workflow is this. We start with this idea that we have a solid solution, a disordered alloy with underlying crystal lattice. We use the coherent potential approximation to average over the lattice site occupancies and describe this homogeneous effective medium representing the disordered alloy. We then use the language of concentration waves to describe atomic scale chemical fluctuations. And in principle, we can use Landau theory. We can apply this Landau-type theory directly on that formalism and learn about ordering tendencies directly. Or we can recover these effective pair interactions, and then we can use kind of whatever flavor of sampling algorithm we would like, you know, Metropolis Monte Carlo or Wang Landau or what have you. Okay, and this means that, you know, in principle, we can for a given composition, we can look at the thermodynamically favored phases, okay, and we can infer short range order, long range order, and so on. Okay, good. So I think I'm a little bit behind time, but that's okay. So what I'll do is I'll talk through maybe a couple of examples, and I can always share the slides later if people would like to look at the examples at the end. So the first,
sorry, can you briefly comment on the specific heat? What are the three peaks? The first is
oh yeah, the heat. Okay,
or the higher one are chemical ordering, right, or something?
This is only looking at chemical orderings. Okay, so what I'm plotting is the configurational contribution to the specific heat capacity. And here, it turns out that there are three distinct orderings that emerge in that particular alloy. So at high temperature, there's an L1-2 ordering with platinum moving to the corners of the FCC lattice, and then actually there's another ordering where because there's a low enough concentration of platinum, that there's an additional ordering on that sublattice, and then finally there's an emergent ordering between the iron and nickel atoms at a lower temperature. Yeah. Okay, so I wanted to give you a few case studies. The first case study I want to talk about is for these so-called refractory high entropy alloys. Okay, and so for a little bit of context, these are the prototypical body-centered cubic high entropy alloys. Okay, so we're talking about elements like vanadium, niobium, molybdenum, tantalum, tungsten. And these are of interest for kind of high temperature, high radiation applications, because all of those constituent elements have nice high melting temperatures, and on their own, they're quite good at resisting being irradiated as well. And the example I want to focus on is on the 4-component niobium, molybdenum, tantalum, tungsten. Okay. So I start by doing my KKR-CPA calculation, okay? And so here I'm looking at the Bloch spectral function, so like the band structure, but for the disordered alloy, and the electronic density of states. And the kind of the feature I want to highlight is that actually two features. The first is that all of these elements are pretty chemically similar, right? So if I look at the species resolved density of states, all of the curves lie pretty close to the average density of states, this black line that I'm plotting here. Okay, but what you find is that niobium and tantalum have a reduced valence compared to molybdenum and tungsten, and that means that their species resolved curve sits slightly below, if you like, the total density of states curve, and that's because they have just one fewer valence electron associated with them, and that'll be important in a second. Okay, if I go away and I do my alloy S2 theory, I do my concentration wave analysis, I find that my minimum eigenvalue is occurring at the H point, okay? And that is indicative of a B2 ordering. So going from the disordered BCC solid solution, A2, to the ordered B2 structure, which is 2 interpenetrating simple cubic sublattices. Okay, and if I apply the Landau theory, my ordering temperature is estimated at 559 Kelvin. Okay, so this wave vector 002 pi over A, that's the H point. And if I look at the chemical polarization, what I see is that niobium and tantalum, okay, minus 0.42, minus 0.57, the concentrations of those elements are going down, when the concentrations of molybdenum plus 0.57 plus 0.42, molybdenum and tungsten, when their concentrations are going up. So what this is describing is niobium and tantalum moving to one sublattice, with molybdenum and tungsten moving to the other. And so this B2 ordering, it turns out, is actually kind of driven by that valence difference between the elements present in the composition, okay? So an element with niobium or tantalum, which has one fewer valence electron, would prefer to be surrounded by the elements molybdenum and tungsten, which have one more valence electron than it. Okay, so fine. And I've got a little cartoon of what that kind of that concentration wave looks like in one dimension here. Okay, but I can go further. I can use these effective pair interactions and do my Monte Carlo simulations. And so this is a plot purely of the configurational contribution to the specific heat of my simulation as a function of temperature. And what I see is that, okay, at high temperatures, so on the right, I have this disordered BCC solid solution. As I decrease the temperature, there's an initial peak in my heat capacity. Okay, and that's associated with the B2 ordering. So with niobium and tantalum moving to one sublattice, molybdenum and tungsten moving to the other. And then at really low temperatures, which are not really experimentally accessible, but they're kind of interesting as a theorist, we find the model suggests that there are these two additional kind of last little coughs in the heat capacity. And what they're actually describing is eventual sublattice orderings on both the on both of the simple cubic sublattices. And you end up with the model suggesting that there is a single phase ground state structure for this system, which is this kind of Heusler-like structure that I'm illustrating just here. And I should say this top left panel. Yeah, did you have a question? Sorry.
So Chris, I just wanted to ask, in this calculation specifically, this is a you're describing thermodynamically equilibrium states.
Yeah.
And so the high temperature phase above the first peak, above 400 Kelvin or so, this is a really there's a single thermodynamic state, no symmetry breaking, no slowing down. This is an equilibrium state, which is really a liquid of particles moving on a lattice, right? Where all configurations are accessible, right? This is a
yes, indeed.
ergodic state, right?
Yeah, absolutely. Yeah.
Okay.
Yeah, because we're doing equilibrium statistical mechanics.
Right,
yeah.
Right.
Yeah, absolutely.
Very good. Very good.
Yeah. So what I wanted to highlight just here is I'm in the top left panel here, I'm plotting the effective pair interactions as a function of coordination shell number, so nearest neighbor distance, and you can see that actually, these effective pair interactions are dominated by the first 2, 3, but by the time you've got out to 6 coordination shells, you've kind of got all the information you're going to get out of there. So there is definitely a finite range to these interactions in most of the systems we've looked at. It's not always true, but in these high entropy alloys, we've generally found that things are pretty short ranged. Okay, so I'm aware that my time is probably fairly close to coming to an end. So I think what I'll do is I'll talk about one more example, and then I will skip the last couple of examples and head to my summary. And as I say, I'm happy to share the slides with people at the end. Yes, okay. The one thing I wanted to say is actually in these refractory high entropy alloys, we've done a bit of work looking at addition of elements like vanadium and titanium. So I gave you that example of just niobium, molybdenum, tantalum, tungsten. If I add vanadium to make this 5-component, what some people call the Senkov alloy, what I find is that actually there's this interesting phenomenon where, because vanadium is a 3D element, the atoms are a little bit smaller, they have a narrower bandwidth. There's charge transfer from the large elements to vanadium, and there's also this bandwidth difference. Vanadium has a narrower 3D band compared to the 4D and 5D bands. And what I find there actually is that instead of getting a B2 ordering, I actually get a B32 ordering, okay? So an ordering temperature is a little bit increased, 742 Kelvin is the Landau theory estimate. The wave vector now is the minimum eigenvalue, if you like, is occurring at the P point, which is pi over A, pi over A, pi over A. And that describes this B32 ordered structure here. And you find that this is dominated by vanadium moving to one sublattice. And essentially, niobium and molybdenum are relatively unaffected by the concentration wave, actually, but it's tantalum and tungsten moving to the other sublattice. Okay, and that's nicely in agreement with the sort of results people have found using other modeling approaches, so things like cluster expansion. So we were very happy with this. We did some work looking at what happened if you included titanium, because some people include titanium experimentally to try and improve the room temperature ductility of these materials. And what we found there was that actually you got these B32 ordering ordering tendencies, as you did with vanadium, but also there was real competition between ordering and phase segregation, which is described by a concentration wave with wave vector 0, or with wave vector the 0 vector. Okay, so that was kind of interesting. And the other thing I wanted to highlight, because I think this is kind of more of a theoretical seminar, is that, okay, this charge rearrangement that I've been mentioning, and I highlighted at the start, okay, the S2 theory is properly accounting for the charge rearrangement. It turns out that really matters in a lot of these systems. Okay, so we can ask the question, okay, what happens if we turn off the charge rearrangement in our calculation? Because the way the theory is constructed, we can do that. We can do what we call a band-only calculation. And if I go to niobium, molybdenum, tantalum, tungsten, what I find is if I turn off the charge rearrangement, the ordering temperature is not particularly strongly affected. But what you find is the minimum eigenvalue no longer occurs at 0.02 pi over a. Okay. It's moved to some point a little bit away from the H point, which is kind of suggestive of maybe longer ranged interactions and a slightly more peculiar ordering. So that's kind of interesting. The real kind of failure of the band-only approximation, though, is in this 5-component alloy where there is this substantial charge transfer between vanadium or to vanadium from the other elements. And there, what you find is if you run a band-only calculation, you predict that the system phase segregates at something like 2000 Kelvin, okay, which is completely at odds with reality. So it turns out that actually, if you're going to do these kind of concentration wave-like analyses, in any system where there is any kind of reasonable charge transfer between the alloying elements, that you really need to consider how the charge rearranges itself in response to an applied chemical fluctuation. Okay. Yeah, okay, well, fine. So I didn't get as far as I wanted to, but that's okay. There are you know, if you want the slides, I'm very happy to share them with you. But what I think I'll do as we're kind of moving close to the end of the time is I'll move to my summary and outlook. Okay. So oh my goodness, what's that? No, there we are, fine. Okay, so I guess I got 3 kind of take-home messages for you. The first is that in high entropy alloys, this CPA does really nicely at describing the electronic structure of the disordered solid solution for very minimal computational cost. It's kind of almost a renaissance of the CPA, these multi-component systems, because it enables you to do things very, very computationally cheaply while capturing a lot of the physics. The second kind of take-home message is maybe that this concentration wave analysis that I've outlined and that I've had time to give you a couple of examples of lets you study these chemical ordering tendencies. Okay, it's not quite as cheap as doing just a CPA calculation for the disordered solid solution, but you can still run it, you know, on a reasonably powerful desktop if you needed to. And the third take-home message, I guess, is that the extraction of this pairwise real space model that lets us do further exploration of the alloy phase space. So I mentioned this idea that the Landau theory lets us get the initial ordering, but by recovering these effective pair interactions, we have this kind of this easing-like model that we can then play with at all temperatures to really start constructing phase diagrams. So the outlook, where I'm looking to go now, is we've started doing some work trying to use these the configurations drawn using this effective pairwise model, using configurations drawn from whatever sampling algorithm you want to start training machine learned interatomic potentials. So generating configurations with realistic short range order to then go away and run a conventional DFT calculation on and include in the training data set of machine learned potentials to try and improve those potentials in some way. So we worked on a stainless steel last year, and that was kind of an interesting project. And the other thing that I'm hoping to get around to is start doing kind of high throughput materials searches. So these calculations are quite cheap, and in principle, you know, it should be possible to screen a few hundred or a few thousand alloy compositions to find those which are most stable, and maybe optimize for particular properties. Okay, the one thing I did want to highlight was that there's quite a lot that goes, there are a lot of ingredients in this modeling methodology, okay? And I can only outline so many of them in an hour. But what I wanted to say was that an extended version of my PhD thesis was very kindly published by Springer Nature. So I went away and I gathered some new results and gave some additional discussion. And if you're particularly interested in the modeling approach, yeah, by all means drop me an email, but you can also find a lot of details in this book or research monograph. Okay, and with that, I should thank all of the people who've been kind of part of this project or this ongoing work. So I did a lot of this work with the support of Julie Staunton at the University of Warwick. We've enjoyed a very fruitful collaboration on this. And even though I'm now at Bristol, we still talk and work together on lots of these things. There are various people at the University of Warwick who've been involved in some level or other. I didn't have time to talk about it, but in some of these magnetic high entropy alloys, Laura Lewis at Northeastern University has been really invaluable in providing experimental perspectives on materials processing. And then more recently, we've done some work with the group of Jan Mina at the University of West Bohemia, looking at particular subsets of the high entropy alloys. Okay, and with that, I will just about wrap up and perhaps let Yang field any questions that might be coming up. Or Marcus. Sorry, Marcus, you're chairing.
Okay, yeah, thank you, Chris. Great talk. Unfortunately, we are at the end of the hour, but if people don't have to leave immediately, if there are some burning questions, please feel free.
Okay, I guess I will ask the first question, and people are welcome to follow up. My question is, can this concentration wave idea apply to magnetic disorder?
Apply to magnetic disorder?
Magnetic disorder, yes. Because you certainly apply that to the chemical disorder, but can that same idea, apply to magnetic disorder?
Yeah. Oh, well, Balash has his hand up because the answer is yes, right? But so the answer is yes, and actually well, I wouldn't say it was easier. It's a different thing, but yeah, this is well known. I mean, this is the sort of the punchline of the disordered local moment picture, where you can infer magnetic phase transitions by considering, if you like, spin waves or magnetic correlations emerging from a paramagnetic state. Yeah, so you're absolutely right. Yeah, you can use a similar approach to describe magnetic phase transitions. Yeah.
Thank you.
You show an example of iron, ferromagnetic iron, nickel, and palladium or platinum. I forget which one.
Yeah.
And so for that calculation, did you include the spin disorder at the finite temperature?
So there's a lot of detail there. So iron nickel, I mean I showed this example for what happened if you put a bit of platinum in, but the iron nickel alloy is really interesting because it has this L10 phase, which becomes energetically favorable or thermodynamically favorable at low temperatures, or relatively low temperatures in the language of alloys. But we've done some calculations, and it turns out that if you include the spin disorder, in a sense, if you describe an iron nickel alloy in the paramagnetic state, that really that L10 phase is barely favored at all. It turns out that actually in iron nickel, it's the lining up of the magnetic moments, it's the emergence of this ferromagnetic order that helps to make the L10 phase thermodynamically stable. Yeah.
Okay. Yeah. Another question is regarding, so for this iron nickel, and you have another alloy element. I think it's palladium. Platinum. And so in this case, you have in this case, you have a very large size mismatch between different alloy element, and presumably it will induce a lot of local distortion. And can you comment on the effect of local distortion on this phase transition in your method?
So the method is always assuming a fixed underlying lattice. So you're not directly taking account of these local lattice distortions. But actually, in multi-component alloys, to be honest, a lot of the kind of these changes to the electronic structure induced by the local lattice distortions, it kind of seems to wash out in the CPA in some sense. And so, although we're not directly accounting for them, if you look at methods where these local lattice distortions are included, we don't do too badly in comparison to them. If anything, the trend seems to be that if you include the local lattice distortions, the ordering temperature is somewhat reduced. And so maybe our estimates are a little bit high, but I think that, I'm yet to encounter a system where not including the lattice distortions is really hurting this approach. Maybe the ordering temperature will be somewhat reduced, but actually the results seem pretty concrete.
Okay, thank you.
Okay, Balash has a question.
Yeah, I just kept thinking about throughout the talk, when you do the CPA calculation, what do you do with the different volumes? I mean, sphere sizes.
Yeah, okay. So what you do, yeah, I mean, I haven't gone into the technical details, but these are always either ASA or muffin tin calculations. Generally, we do ASA, although in principle you could do muffin tin as well. What you do is you you fix the sphere sizes the same for all elements. Okay. And really what you do, so you've got two options. Either you you fix, let's say, the experimental lattice constant. So if you've got a nice experimentally determined lattice constant, what you do is you freeze your FCC lattice that's having that lattice constant, and you do your ASA prescription, and you give all elements the same sphere radii, the same Wigner-Seitz radius. You can also, if you're feeling brave, you can find the cell volume that minimizes the energy. Or if you're feeling even braver, then maybe you could do some kind of Debye model and account for the thermal expansion and get a lattice constant ab initio. But even then, you would be holding all the sphere radii the same. Yeah.
Okay.
What's it?
Yeah. So at the very dead end, you talked about machine learning for improved potential in the mechanism. So maybe I will write to you. This is a technical question. How will be the training data set would look like? Like what kind of data set you want to make?
So I mean, this is something we've only recently started to get into, but essentially what we're interested in is potentials where for alloys where there's a degree of atomic short range order present. And it turns out that if you just train your potential very often if you just train your potential on perfectly disordered configurations, if you like, so the sort of configurations, lattice-based configurations you would get, say, using an SQS type method, you don't show the potential, if you like, the short range ordered structures or the long range ordered structures, which are lower in energy than perfectly disordered structures in some sense. And so what we can in principle do is run some kind of fast metropolis Monte Carlo type simulation at a given temperature and look at kind of extract some configurations which have kind of what we believe is representative short range order that you can then go away and do a DFT supercell calculation on and include in your training data set energies and forces. So it's really about showing the potential, I guess, more chemical information, showing it, okay, which,
so the training data set, your model will trained on what are the features in that data?
Okay. So, no, this is a huge area. So this is like a whole separate seminar all on its own.
Yeah, I understand. I will write to you. It's a very
by all means, write to me. So there are many ways of doing this. I have worked in the past with people who use a variety of means of doing this. Generally, what you're doing is looking to represent the local environment around a given atom. So you're constructing, as you say, you're constructing what you believe to be kind of physically meaningful features, describing local atomic environments, and then you're doing machine learning on those in some very abstract sense. Yeah,
maybe I'll write to you. Thank you.
Yeah, by all means. Yeah, I can send you some papers. Yeah.
Okay, Mike.
So you say that you also have a version of this for magnetism, and I wonder, do you?
Well, I don't, but other people do.
Okay.
Well, I mean, I do, but it's not something that I've developed, right? That already.
Okay. Well, so the reason I was asking is that I think there are cases where there's important coupling between the compositional and magnetic degrees of freedom. For example, in chromium containing high entropy alloys.
Yeah, for sure.
So maybe if others have looked at this using concentration wave methods, say in the Cantor-type alloys, for example.
Yeah, so I think this is a really interesting question. So I did have an example sort of towards the end of my case studies where we looked at this. At the moment, we're limited to freezing the magnetic state. So we either do a DLM calculation where we're considering kind of complete spin disorder, or we do a conventional collinear spin calculation where we're assuming, if you like, perfect magnetic order. And what we do is we freeze the magnetic state and then we do the concentration wave analysis. But actually, you're absolutely right. There are alloys where there's a level of coupling here, and it's not reasonable to do that. And in principle, it's perfectly possible. What you would have to do is do a DLM calculation in some sense where you had partial magnetic order emerging, let's say, and then you would have to apply the concentration wave analysis to that. In principle, it's doable. It hasn't been done yet. So, you know, if someone's going to give me some money, then maybe I'll go away and try that. But yeah, I think you're absolutely right. There are certain cases where this matters, and freezing the magnetic degree of freedom, which is the assumption we've often made, is maybe not quite the right approach. So, for example, in iron nickel, I think it would be really interesting to show how you know, the L10 ordering became increasingly favored as the magnetic moments gradually began to line up in some sense. Yeah.
Mm-hmm. Yeah. Thank you.
Vishnu?
Thanks.
Yeah, I mean, thanks for the talk. It was really fun listening to it. I was confused on the level of correlation that's present in comparison to, say, the cluster variation where you have a pair correlation 3-body and 4-body. So is that the same level of correlation that's present in the concentration wave as well?
So in principle, you have access to the higher order correlations in some sense, but when we go to this effective pair interaction, we are just looking at pair correlations. So in principle, we believe it's possible. We had a reviewer actually ask us this on a paper a little while ago. In principle, we believe it's possible to do this. It has been done in the magnetic sort of, if you quote unquote, concentration wave or spin wave formalism, where you get access to higher order interactions. We haven't done it yet, but yeah. So at the moment, the effective pair interaction is pairwise, and if you like, the second derivative terms are kind of they're giving you direct access to this 2-point correlation function. But yeah, at the moment we're not considering like 3- and 4-body correlations explicitly.
And do you think it's worth like going to like a full potential CPA compared to muffin tin or ASA?
Yeah. So this is a good question, right? So it would be wonderful to do full potential, but it would be challenging. I mean, the mathematics. So I think, you know, if you look at the mathematics, if you wanted to do it, say, band only, maybe it would not be so bad to do full potential. But I think it's doable, right? Of course it's doable, but it would be challenging, I think, to do full potential. I mean, it's not to say that it can't be done, it just hasn't been done yet. But yeah, it's once you start worrying about the charge rearrangement, charge response, the set of equations that you have to solve gets quite complicated quite quickly. And, you know, whether it's worth it, you know, whether you really believe you need to do it is a question. And then, yeah, whether you want to sink the time into doing that is another question. I mean, generally in these closed packed systems, in these high entropy alloys, you really don't gain that much from going from the ASA to say going to full potential, but there might be systems where you would want to do that. So yeah.
Yeah, thank you.
So I believe it's possible, but it's not been done yet.
Right, Vlad? No, you mute. You unmute. You're muted.
I'm sorry. My first question. First of all, let me say I really enjoyed this talk because many of the ideas that you described concerning the wave, concentration wave, and so forth, the parallel is something that we've been discussing within Master quite a bit, and it's a beautiful development which I really I enjoyed. I didn't know about, and I think it's very promising. But I have a specific questions. So the first question is, you know, when you talk about your eigenvalue analysis, this is very similar to eigenvalue analysis within Landau-Gisberg theories, but this usually implies a second order phase transition. If you have a robust first order phase transition, then this kind of analysis will tell you about the lower spin order. In other words, it's a lower bound on the transition temperature. It's not exactly correct. So did you? So that's my first question. Second question is, if you have many components, you talked about 4 or 5, but if we can imagine having 10 or 10,000, you know, in statistical mechanics, we have models where, for example, the spin components can be, instead of 2 or 3, can be taken to be n, and then in the large n limit, their statistical mechanics can be solved in an approximation that this becomes exact in the large n limit. So do you think that, so this question is, if you have a large number of components, does it offer? Can we actually more systematically solve the statistical mechanics? And the third question is, there's also SQS in addition to CPA, and we have actually explored within MAST also try to compare CPA, SQS, and LSMS. But what's your perspective? Because a lot of people are chemists. We have some chemists at FSU who do SQS with machine learning on tens of thousands of structures and so forth. So how do you? So probably my most burning question is, how do you compare SQS to this?
Yeah. Okay. Remind me what your first question was. Your first question was
the first question was about spin order. I mean, these eigenvalues
oh,
are
yeah,
not
yeah,
really...
yeah. Sorry. Yes. Yeah. Okay. So no, this is a very good point. So yeah, this Landau-type theory that we're using, you're absolutely right. If you have a first order transition, in principle, this Landau theory is not the best way of examining the ordering. The counter argument or the solution is to say that, well, when you recover these effective pair interactions, you can then do Metropolis, Monte Carlo, Wang-Landau sampling, whatever,
sure.
And then based on those effective pair interactions, which you're getting from the concentration wave analysis, you can look at either first order or second order phase transitions.
Oh, of course, and they are more advanced. There are more advanced versions of Landau theory that can be invoked.
Yeah, indeed. So yeah, exactly. So yeah, in principle, you could look to extend, to some level of theory, which would look after the first order transitions. Kind of the pragmatic solution that we've been taking so far is just to use these effective pair interactions which come out of the concentration wave analysis, and then you're happy because you can look at whatever orderings you would like. Okay. Your second question was about this exact solution in large N.
Yeah.
Well, it depends how large N is, right? I've only got 100 or so elements to play with. So if 100 is a large enough N, then...
Well, it's a question of principle. I mean, when they use a large N method in the context of rare earths, right? They have a spin is not 10,000, the spin is 7/2, but they use 1 over n as a small parameter, and then they apply it to finite N, right? With very good success.
Yeah.
Right? So in principle, if some approximation is valid when N is very large, well, probably it's going to be pretty good when it's 5, right?
Yeah. Okay. It's not something I've looked into. I mean, if you've got some references that you could send me, I would have to look into it.
No, I don't think there are any references. This is something I would like to work on, but I was just curious if someone else thought about this.
I am not aware of anybody who's thinking along.
Actually, no. We have a chemist in our university who does SQS, and he actually tried to use different large N's and to calculate these high order terms. You're talking about pairwise interactions and high order terms, and he found that these high order terms in this cluster expansion are minimized when N becomes large. But this is a numerical, empirical observation. It's not a result from formal statistical mechanics.
Sure. Yeah. I mean, a lot of the time we've had to be a little bit pragmatic with with this, and so you get your effective pair interaction, and you see what comes out. But yeah, it would be interesting maybe to think about these things. Yeah, whether maybe, I mean, I guess I mean, how many elements can you include in a high entropy alloy? Most people don't seem to be going beyond 6 or 7. I mean, I guess the Gibbs phase rule eventually kind of says that there is there's a limit to the number of elements you could consider alloying. I mean, so just for context, I mean, so for example, the Cantor alloy, that 5-component alloy, the samples where that Cantor alloy was discovered, certainly in the group of Brian Cantor, were samples where they were trying to alloy 10 or 20 elements. Now, the solid solution was only really emerging, with 5 or 6.
I see. That's very interesting to know. Yeah, I didn't know that.
Yeah.
And what about SQS? What about SQS?
Yeah, so SQS, yeah, fine. I mean, listen, the SQS methodology is very nice if you want to learn about the electronic structure and so on, and if you want to learn about information about a disordered alloy. I mean, if you want to infer, short range, if you want to look at short range order and infer phase transitions, then in principle, what you're going to do is some kind of, you're going to build a big supercell and you're going to apply an appropriate sampling algorithm, and your energies are going to come from DFT, or they're going to come from an interatomic potential, or they're going to come from cluster expansion if you've trained that. I mean, it's all doable and it's very nice, and it's just quite computationally expensive. And you know, I think what we're doing is just different. I'm not saying it's any better or any worse. What I will say is it's certainly much computationally cheaper.
That's what I was actually wanting to hear. Can you get relative? I mean, I'm not asking for super accurate results. Relatively crude results, but much faster than SQL.
Oh, yeah.
Is that the fact? That's a fact.
Yeah.
Right?
Oh, yeah. No, I would. Yeah. Okay. So I haven't really talked about specific computational costs here, but if you give me a 5-component alloy, let's say, you know, you cook up a 5-component alloy. Well, I mean, and actually it doesn't really scale with n. I mean, matrices get bigger, but the core of the calculation doesn't grow with n. If you give me an alloy, I'm going to do a self-consistent calculation. That's going to take me 1 or 2 core hours because I'm working in the primitive unit. Even if I really go crazy with my K-point sampling, it's not going to be expensive because I'm working with the primitive unit cell. Then if I do the linear response calculation, to get, you do this concentration wave analysis, right? And I learn about the, you know, the energetic cost of chemical fluctuations. That is probably taking me, I would say 50 to 100 core hours. You know, that's if I want to be really robust and make sure, you know, everything's nice and tightly converged. I mean, if you can do something fast and dirty in a bit less time, but yeah, 50 to 100 core hours. And from there, you've already got the Landau theory. If you want to do the Metropolis, you know, a Monte Carlo simulation using the effective pair interactions, you know, fitting the pair interactions is like, you know, it's done like that on your laptop. It's a pretty simple fit. And then, you know, and if you know, you're talking tens to, you know, maybe 100 core hours that you could have a decent Monte Carlo simulation. So you know, end to end, for a given alloy, you're talking under 250 core hours. You know, probably less if you wanted to be, you know, a little bit fast and loose with the convergence. So, but if you wanted something really robustly converged, then easily, yeah, 250 core hours would be enough on a typical cluster. And so I guess what I'm saying is that, you know, you can do this entire analysis for kind of a similar cost to doing a single, you know, geometry optimization on a DFT supercell, right? So I guess the point is that yeah, maybe it's not, you know, we haven't got things like local lattice distortions in the approach, but it's so much computationally cheaper that maybe you can get, you know, useful information out for very little computational cost. Yeah.
Fantastic. Very nice. This was super interesting and I learned a lot. Thank you so much.
Thank you. Thank you for coming.